Welcome back to this course on polymer chemistry. In last lecture we were discussing about polymer properties and their evaluation, and we did a detailed discussion about mechanical properties, and we also discussed about thermal properties and little bit of fire resistant properties of polymers. In today's class what we will do is to go through the other properties like optical properties, electrical properties, barrier properties and environmental properties, surface properties, and not in detail, just briefly, and then begin our discussion on chemistry of polymer additives. So, let us start our discussion on optical properties. Now, when you make a material out of a polymer like plastic material, now the look, the aesthetics of the material or the parts depends upon several optical properties. For example, if we are going to make a plastic material or polymer material which are intended to be a optically clear applications, then the plastic part or the polymer part has to be transparent, and if it is for absolutely clear application, then there should not be any haze or any yellowness in the material and so on. And in opaque applications there are other properties like gloss, reflectance, yellowness index and so many things, surface roughness. So, those are the things one must consider before before you apply or before you have a polymer product out in the market. So, if we look at these optical properties of a plastic material, you can list a number of terms: transmission, diffraction, reflection, scattering, absorption, clarity, haze, gloss, yellowness index, birefringence, color and so on. So, what I am going to do is not to discuss each and every term, but to pick up few important terms and then explain and then see how the value of that particular property or value of that particular parameter depends on the chemical structures. For example, let us talk about transmission first. Now, what happens when a light travels through a matter? If you are talking about a plastic material, obviously you are talking about you are thinking a plastic material or polymer material. When light travels through a polymeric material, what happens? Obviously, first thing happened that when it just hit the polymer surface or the part surface, it can get scattered from the surface of the polymer if the surface is rough, and of course reflection, part of the light gets back to the original medium by reflection. So, basically when a light travels through a material, in this case a plastic material or polymer material, first thing happen is surface scattering or reflection, and because of that there will be loss of intensity of the light passing through the material, and scattering from rough surface also will lead to reduction in the clarity of the material and of course increase in the haze. Now, we will discuss or define this term clarity and haze in a minute. So, basically because of surface scattering and reflection, your transmission comes down. In the bulk, what happens? In bulk there could be two things happening. One is scattering can happen, and now because of scattering there will be loss of intensity of light, and molecular absorption can happen due to presence of some chromophores or some pigment in the material, which could lead to formation of color in the medium. So, because of scattering and absorption, there will be loss of intensity. So, the bulk extinction coefficient is consist of bulk scattering and molecular absorption. It may be noted that this absorbed light can be re-emitted, but that re-emitted light is always less or at best equal compared to the amount of absorbed light. So, there will be a drop in intensity when light passes through the matter due to surface scattering, reflection and bulk extinction. Now, let us discuss little bit about this bulk scattering phenomena, which happens very frequently in a polymer material. Now, the scattering happen due to inhomogeneities in the refractive index in the medium. So, if there are inhomogeneities present in the polymeric material, there could be or there will be bulk scattering. For example, if you have some particles, so small particles which are there or voids or some air bubbles are there, then in a homopolymer matrix, then there will be differences in the refractive index between the medium and those portions which I just mentioned. So, there will be scattering. So, scattering to happen, the two conditions has to meet. One, there should be difference in Ri refractive index between the scatterer and the medium. Obviously, if there is a particle present in the medium whose refractive index is same as the polymer refractive index, then there won't be any scattering happening. So, first and foremost criteria for scattering to happen is that there should be a mismatch or inhomogeneities in the refractive index between the scatterer and the medium. Second, obviously, the amount of scattering will depend upon the size and the shape of the scatterer. The more the size in comparison to the wavelength of the light being scattered, the higher would be the amount of scattering. For example, presence of crystalline phases in a semi-crystalline material, the amorphous and the crystalline phases will have different refractive index. So, that will cause scattering, and for this reason actually most of the crystalline polymers are opaque in nature because of the heavy amount of light scattering. If you have fillers which are having higher size compared to is not very small size, have a significant diameter, then they will scatter light. Immiscible blends or block copolymer also have difference in the refractive index between the two phases formed by the two homopolymers or two blocks, they will also scatter. And liquid crystalline polymers, because there are different inhomogeneities in the refractive index for a liquid polymer, crystalline polymer LCPs. Now, for a single component polymer, say for example, there is a homopolymer you are talking about or a copolymer, miscible copolymer, they can also scatter slightly due to presence in spatial variation of Ri, due to presence of some stresses, molding stress, or some reason there could be some maybe very small, but small inhomogeneities in the refractive index value across different places of the material, and for that reason there could be slight amount of refractive index. So, if you want to make some polymeric material which does not or should not have any scattering, then your material must be very homogeneous in respect to the refractive index value across the entire medium. And as I said, the presence of impurities like voids, bubbles, etc. may also cause scattering. Obviously, the refractive index values between the material polymeric matrix and the voids or the bubbles will be different. So, depending on the size of these whites of bubbles, they will scatter light. Let us take a real example of block copolymer of BPA polycarbonate and PDMS. This is a structure of the block copolymer, where this block consists of a PDMS block and a bisphenol A polycarbonate block. Depending upon which is higher, this polymer may behave as elastomer or thermoplastic. If the amount of rubbery phase, that is PDMS, is higher, high siloxane percentage, then this polymer behaves, block polymer behaves as elastomeric, and if the amount of siloxane is lower, then this block copolymer behave as thermoplastics. Now, let us talk about low concentration of siloxane, say about 5 to 10%. We are talking about thermoplastics. Now, because this PDMS is stitched with the other block, then they do not phase separate in such a way that they come out or delaminate from the total matrix. So, they make this PDMS form small domains of PDMS in the entire matrix, which is mostly BPA polycarbonate. We are talking a composition where it is mostly BPA polycarbonate and maybe 5% is PDMS. Look at the refractive index of these two. PC has 1.58, PDMS is 1.4. So, obviously, there is a mismatch in refractive index. So, they will scatter light, and depending upon the amount of scatter, the transparency will come down, and higher the scattering, the transparency will be less. Now, look at the transmittance TM or transmission electron micrographs. These black portions are the siloxane domains and the background is the BPA PC. Now, in this case, this A, the block length of PDMS is higher. As a result, these domains sizes are higher. So, it scatter more and the transparency is transparency very less. In fact, this is opaque, whereas when the block length is small, then they also scatter, but the size, because of the size is so small, their scattering amount is low. So, this block copolymer, the polymer material made out of this block copolymer will look transparent, but slightly hazy. So, if you look at the optical properties of polycarbonate, light transmission is more than 88% for this 3 mm thickness plaque, and haze is about 1%, whereas in block copolymers B, where the domains are having smaller sizes. So, the scatterer size is very small, their transparency has come down because of scattering, but not that much. Haze has gone up, whereas when the scatterer size is much higher, then the polymer is become completely opaque. So, basically what I again telling that the scattering amount of scattering depends upon the refractive index mismatch. If there is, you can make a block copolymer or a two phase system where the two phases same refractive index, no matter what is the size of the scatterer, it will not scatter. But if there is difference in refractive index, the higher is the size of the scatterer, it will scatter more and it may turn opaque, whereas if the scatterer size is small, it will scatter less. So, there will be drop in transparency, but it will not, may not be opaque. Now, let us talk about little bit about the transparency of a polymeric matrices. Now, we just learned that when light falls, say in a plastic material or any material, there could be three possible phenomena happen. One is the scattering or reflection from surface, second is the scattering, bulk scattering, and third is your absorption. So, the total flask of the light coming in there will be part of light which will gets transmitted. Now, if I consider phi as the intensity of the or flask of the incoming light, and so this is the flask of the incoming light, and if I consider phi un is the flask of light transmitted undeviated from its original path. Then percentage of transparency is given by the fraction of light transmitted undeviated through the matrix. Now, we can also write that the light, the flask of the transmitted light which went out undeviated would be phi is the flask of the incoming light minus the phi due to reflection from surface minus phi scattering in all direction. We discussed about what is the cause for scattering, and phi absorption. If there are some moieties or some chromophores which absorb light, then it will absorb light and that will decrease the intensity of the flask of the outgoing transmitted light. This might give you color in the medium. Now, these two depends on the thickness of your material and also the lambda, the wavelength of the light which are used. So, obviously, this value percentage and hence the percentage transmission will also depend upon the thickness and the lambda of the or the wavelength of the light used. Now, if we have no scattering or no scatterer present in the medium, in the polymer material, and also there is nothing which is absorbing, then obviously this transparency is only given by the loss due to the reflection. So, if we can find out theoretically what will be the extent of reflection, then we can find out what will be the maximum transparency of any material or a plastic material, and that is theoretically given by Fresnel equation. So, theoretically from Fresnel's equation, the maximum transparency is given by this, where n is the refractive index of the polymeric medium. So, obviously, if we talk about, say, for example, take case of PMMA, polymethyl methacrylate which has Ri 1.49, then percentage T maximum. So, the maximum percentage T of a PMMA, if you put this value here, it will come around 96%. So, this is the maximum transparency you can get out of a PMMA material. So, the higher is the refractive index, lower is the maximum transparency one can get when a light pass through a polymeric material, but one can never get this high amount of transparency through a polymeric medium, because there will be some inhomogeneities in the refractive index in the medium, even though this is for a homopolymer, and that will cause some amount of loss of flash of the incoming light or transmitted light due to scattering. So, maximum transparency for a PMMA in real case we get about 92.8%. So, that 3% transparency is lost due to presence of scatterer, and this value is for lambda around 380 nanometer to 110 meter. So, if lambda changes beyond that, this value might change. So, what we learn from here, that the less the, if there is no scatterer present or nothing is present here which is absorbing light in the polymer matrix, then the transparency is dictated mainly by the value of the refractive index. So, if you compare say like PMMA with a BPA PC which have a refractive index value of around 1.594, then obviously the maximum transparency possible for a PMMA is higher than a BPA polycarbonate. So, if you want to make a transparent, or if you want to increase the transparency of a polymeric material, then you should look for a polymer which have lower refractive index. Now, what is refractive index? It relates to the polarizability of the molecules present, and that order of polarizability depends upon normally the size of the groups present. So, the polarizability of different groups will be of order like this. So, the values of refractive index, if I write, then say PET, polyethylene triethylamate, will have a value of say 1.64, PC we just write 1.594, PMMA 1.49, and say PTFE, polytetrafluoroethylene, will have even lower refractive index. So, if the polarizability is less, the refractive index will be also lower, and if you want to make a transparent polymer, then obviously for a given thickness and for a given wavelength, it is always preferable to use a polymer having lower refractive index than a polymer with having a higher refractive index. So, we just discussed about the transmission. Now, talk about haze. Haze is defined as the percentage of transmitted light which is passing through the specimen deviates from the incident beam by forward scattering. So, obviously, if there is something present in the medium polymeric material which is scattering, and it typically scatter in all the direction, then the amount of forward scattering amount of light which is scattered is and which deviates from the incident beam by forward scattering is what is haze. Now, for calculating or defining haze, we will only consider the forward scattered light flask which deviates more than 2.5 degree on average than the incident light beam. So, with the lights, the forward scattered light which is scattered beyond 2.5 degree compared to the incident light would be taken as the value for haze. And haze characterize the loss of contrast that result when objects are viewed through the scattering medium. So, example, if it is a loss of haze because of haze loss of contrast. So, if you are using two plastic material to view these two, then obviously there will be loss of contrast if you are looking through a hazy material. Now, haze is caused by both surface scattering and bulk scattering, and you can remove, if you want to know what is the contribution from surface and bulk scattering in the haze, then what can be done? You can actually dip that plastic material in a liquid of similar refractive index. Now, in that case, that will minimize the surface scattering, because the surface is now smooth because they are dipped in liquid. So, the haze will be mainly because of the bulk scattering. So, now from that value you can actually distinguish between, or you can find out what is the contribution from surface scattering and bulk scattering on the haze value. What is clarity? Clarity is the ability of the sample to transmit the fine details of a object viewed through it. It's basically is a resolution, how good resolution you can get when you viewing through a plastic material. So, if the clarity is less, then the material or the resolution will come down. So, a material, if you look through a material which has lower clarity, then your resolution of the object will come down. It is strongly related to the angular distribution of scattering light as scattering intensity, and if the size of the scatterer is large, then the angular distribution of scatter intensity will be higher. So, it is always prefer to have to minimize the size of the scattering center to get maximum value of clarity, and obviously it depends on the distance between the object viewed and the sample, and if there is light absorption and scattering, obviously clarity will be lost. Next terms we will be discussing about reflection and gloss. Reflectivity is defined as the ratio of the intensity of the reflected light to the incident light. So, the more amount of incident reflected light, more reflection means the reflectivity will be higher, and that depends upon angle of incident of the light and angle of refraction, which in turn depend on the refractive index of the medium. So, in this case also, if your refractive index of the material or polymer is higher, then the reflectivity is also higher, and if your angle of incidence is higher, the reflectivity is higher, and this reflectivity is given by this expression where alpha is your angle of incident and beta is your angle of refraction. Gloss relates to the reduction of intensity of light scattered specularly off the surface. Specularly means the angle of incidence is same as angle of reflection like a perfect mirror. If a surface is not smooth, say it has rough, then the lights which are getting reflected specularly from different region, they will have different distance to travel to the observer. So, there will be phase difference, and as a result there will be decrease in the intensity. So, if the sample is rough, then the amount of or intensity of the light which is specularly reflected will be lower, and there will be reduction in the value of gloss. So, it is better if you want to make a glossy surface, then the surface should be smooth, and also if the sample is having a larger refractive index, then as a result of higher reflection value, your gloss will be also higher. How do you measure gloss? Gloss is measured or related to the intensity. It basically measured as the ratio of reflectivity of a sample to the reflectivity of a standard, and typically the standard is taken as a optically flat black glass for a particular incident angle. So, basically if this is considered a perfectly reflecting material, then the reflectivity compared to this for a material would be given by the, or will give the value of gloss. So, gloss will increase with the increasing refractive index, as I discussed that with the increase in refractive index, the amount of reflected light is higher. So, obviously gloss increases. It increases with the angle of incidence. Gloss decreases with roughness. Obviously, the reason I said that the distance traveled from the surface to the observer will be different from different region. As a result, there will be phase difference and intensity will come down. And if there is a optical homogeneity is just beneath the surface, obviously the amount of light scattered and reflected will be different, and the gloss will come down. And other factors like polymer surface morphology, processing parameter, mold finish, which will give us the smoothness of which basically dictates the smoothness of the molded parts. So, they also affect the value of gloss. For example, blending of rubbers usually lead to decreased in gloss in case of crystalline polymer like polyolefin. So, we know we now discussed what is haze, clarity, reflection and gloss. One more term we want to discuss in optical properties, birefringence. Birefringence is basically optical phenomena which where sample exhibit different refractive indices for differently plane polarized light. So, the refractive index value for two perpendicularly polarized light will have different value. So, crystalline polymers, they have different refractive index in particular perpendicular direction. So, they will have different values. So, they will be birefringent. In terms of molecular level, the polarizability in one direction and the perpendicular direction, say for example, one very high aromatic polycarbonate where they are different. So, they are molecularly birefringent, but we do not measure the molecular birefringent, we measure the macroscopic birefringent for a sample, and that is given by the difference in the refractive index in the two different direction. So, if this is not 0, then we consider the sample is birefringent, and for very optically useful material, it is recommended that the birefringence should be lower. Just briefly talk about the electrical properties of polymers, and we just talk about electrical conductivity, and We know that most polymers are insulating, and so they are dielectric, and polymeric dielectric are used in capacitors and as insulators. So, basically these are the two main use of polymers in electrical samples. And the values of the electrical conductivity, you have the normal polymers like polyethylene, polystyrene, they have values of electrical conductivity just like insulator, whereas the other end, extreme other end, the metals which are having much higher conductivity and they are perfect conductor. And in between there are few polymers which are highly conjugated polymers, they have conductivity in the range of for semiconductor, and they are called conducting polymers, and they are basically not the commodity, or they are not produced in large amount, they are very they produced in small volumes, and we are not going to discuss much about conducting polymers. The only thing what I want to mention is the examples of few conducting polymers like polyaniline, polypyrrole, and structures are given here. Next, we want to discuss a little bit in brief the barrier and permeability of the polymers. Now, think about that you are making a packaging material out of polymers. For example, if you are taking a perfume bottle, then if you want that the perfume to be remain in the bottle for as long as possible. So, you want the polymer material to behave as a barrier to that perfume whatever is there in the inside. For example, polymers are heavily used in as a packaging material for foods, and there are so many other applications, and for that it must have some properties. And for foods, basically they has to be flexible, they has to be transparent, and they also have a specific barrier properties. So, barrier polymers are having low permeability coefficient and restricted passage of gases, vapors, and organic liquids, and the polymers in barrier applications like packaging industry, their demand is growing day by day for preserving flavor and safety of food product. Now, permeability is opposite to the barrier. Basically, more permeable means less barrier, or more barrier means less permeability. The permeability is defined as the product of solubility of a gas or vapor in the polymer matrix and its diffusion coefficient. So, basically permeability is given by two factors: the solubility of the gas or the vapor in the polymer and the diffusion coefficient of the gas in concern, and it is measured as the permeability is measured as the rate of transfer of the vapor or the gas per unit area of the material and per unit pressure difference across the film thickness. So, basically is normalized with the area as well as the pressure difference across the film thickness. However, plastics are still not as good as barrier materials like glass and metals. So, there is still necessity of making plastics materials which can be as effective as like glass and metal for barrier applications. So, we just said that the barrier or the permeability properties of polymer depends upon the diffusivity of the gas concerned, and of course, the solubility of that gas in the particular polymer. Now, diffusivity of the gas depends upon chemical structures. So, it does not only depend on the molecular structure, but also on the crystallinity and crystal morphology. In a semi-crystalline polymer, crystalline regions are highly dense region, and basically it acts at a very high barrier to any diffusion through it. So, basically higher the crystallinity, higher is the barrier property for that polymer. And in fact, if you increase the density of the polymer matrix, the barrier property goes up. So, if the high free volume is higher, which means there are the free regions where the gas can diffuse through, which means the diffusivity will be higher. As I discussed, the higher the crystallinity, crystalline regions are impermeable, hence lower is the diffusivity. Higher is the tortuosity, lower is the diffusion. Tortuosity means is the path one has to travel to cross that thickness. So, if I consider one example, now if I have a polymer matrix and there are, so this is, for example, compare a polymer matrix, just plain polymer matrix, and a polymer matrix with all these are, say, for example, clays. These are clays which are exfoliated in the matrix. Then if a gas has to pass through this medium, then it has to take longer path like this compared to a path where you do not have these clay materials. So, this means this is a tortuous path, and higher is this tortuous path, the higher is the barrier to the gas to pass through. And if the diffusivity increases with the decrease in the size of the gas molecules, obviously for well known reasons. So, transmission is follows for everything is same, given everything is other things is same, the transmittance rate will go up for a smaller size gas compared to a higher size gas. Second parameter which is responsible for permeability is the solubility, and solubility of a gas in a polymer depend upon the chemical affinity between the gas and the polymer we are talking about. Now, that depends upon the solubility parameter of the gas and the polymer matrix. We discussed earlier when we discussed the polymer solutions, we talked about the solubility parameter. So, basically the higher the solubility, it is higher is the permeability of the polymer matrix towards that gas. We also briefly talk about chemical resistance. Chemical resistance is basically a property where a polymer is bring in contact with certain chemicals, and after a given exposure time the property retention is measured. So, if you are talking about some mechanical property, then after the exposure the mechanical property like impact, tensile strength, those are compared with, or ductility, those are compared with the value which was before the exposure to the chemicals. And if there is less deterioration in the value of those property, then the polymer will be resistant to chemical. So, this is as simple. You can talk about mechanical properties or optical properties like gloss, haze, with in contact with the chemical, that optical properties might change as well. And the resistance of the polymer to various chemicals depend on number of criteria. Obviously, it depends on the chemical structures. For example, if you have a hydrolyzable groups, if you bring contact if you bring that polymer in contact with say acids or bases, then it will hydrolyze, and as result molecular degradation will happen, the properties will come down. Similarly, if should not react with the chemical you are bringing in contact with. Solubility of the polymers with the experimental chemical, obviously to be resistant the polymer must not be soluble in the experimental chemical, and that depends on the crystallinity and the morphology. The higher is the crystallinity, normally the resistant to chemical is higher. So, crystalline polymers are much more chemical resistant than amorphous polymers. If you have a molded in stress, like while molding because of some other reason, because of not good flow in the material, you have built in some stress, then obviously in any given opportunity the polymer will try to release that stress, and one opportunity, if it come in contact with the chemical, it might release that stress by cracking or crazing also. So, molded in stress is basically bad for a polymer to be resistant to a chemical. While testing, there are several test parameters must be considered for comparing the chemical resistance or resistance of different polymer. For example, time of the contact with the chemical, temperature at which you are doing the experiment, the stress level, what is the external stress you are applying during the experiment, concentration of the chemicals which are using, type of exposure, whether you are just contacting or immersing in that particular chemical. So, these are all the parameter has to be standardized if you want to compare between the chemical resistance of different polymers for a particular chemical. If you want to make a plastic bottle for a perfume or say something else like alcohol, then obviously that plastic material has to be resistant to that alcohol to be survive for long time. So, these are the typical application where you test for chemical resistance. Chemical resistance, obviously chemical exposure may result in physical degradation, stress, cracking, craze, swelling, discoloration, so many things can happen, and obviously it can do chemical attack and bring down the molecular weight, and if you decrease the molecular weight, obviously there will be loss of lot of properties including mechanical properties, thermal properties and so on. Just briefly discuss the weathering of polymers. If lot of polymers are used in outdoor applications. So, to understand how long they will survive in that condition, outdoor condition, you must know the weatherability or the mechanism which the polymer gets weathered. So, weatherability is basically nothing but the retention of property of a particular polymer after it has gone through or it has stayed in outdoor weather for some amount of time. So, the higher weatherability means it will retain, the polymer will retain the properties for a longer period of time in that given weather condition. What are the conditions in the weather which affect the polymer properties? UV radiation in most extent, and that will depend upon which season you are, winter, summer, what is the exposure angle, latitude, which latitude your polymer is exposed, heat cycles. So, that will depend upon what temperatures, what is your air temperature and so on, the moisture content in the environment, and that will depend upon the rain, condensation, humidity, It will also depend upon acid, rain, other pollutants. So, all these things contribute to the weathering of polymers to different extent. For example, UV radiation is the most important parameter for responsible for weathering of polymer. So, the decreasing importance is this way. So, if you want to compare the weatherability of different polymer, you must have a standard conditions which is very difficult to reproduce, and you must compare a conditions depending upon looking at the final application. Basically, you cannot say just your polymer is weatherable or not. So, your polymer can be weatherable or not depending upon where it is used, in which place and which condition and so on. And these all factors which are I listed here, it may not be responsible, have different response. So, different polymers response to these factors will be differently. So, there is no uniform test condition as I was just mentioning. So, it will depend upon the final outdoor application where these polymers are used. So, what I will do, I will stop here for this lecture, and in the next lecture I will start the discussion of polymer additives and some of the additives which are used to basically protect the polymers from these weather conditions, including say UV radiation, and some additives which might be useful or added to the polymer to increase the performance of the polymer. So, let us stop for this lecture, and I will start the discussion on polymer additives in the next lecture.